Before I start, I want to ask one stupid question. Do you know what DataStream is? Anyone know what DataStream is? No? Nobody? Okay, second question is, anyone know what what Streamhouse is? You just heard the name Streamhouse, right? A few minutes ago. Okay, there's one. Perfect. So today I'm going to talk about what Streamhouse is and why and when you should decide to use Streamhouse and how to use it from concept to technical implementation. I'm also might use some time to talk about what the company Ververica is and who we are, where we came from, and where we are leading to. So let's start. 2023 is a special year for Apache Flink because we won the SIGMOD System Award. This is fantastic because it means the beginning of a new era. And Ververica is the company behind the whole development for years. So we are so grateful, and we want to thank each and every single one of you for your contribution. So without your effort, we cannot get this award. Thank you. Flink is hitting records every year. So we are one of the hottest projects in the open source project. And in the operation environment, there's many amazing numbers. The size of single cluster breaks 2,000 nodes. And the biggest Flink infrastructure I know in one company contains more than 4 million cores. And more than 4.1 billion events can be processed within 1 second. So when you are using Flink, you should not have any concern about the scalability. It has been proven. And in the past few years, many industries started using Flink to make real-time business decisions, like finance, game, logistics, healthcare, you name it. There are a lot of sophisticated solutions that have been built, like personalized recommendation, risk control, that affect everyone, almost everyone of us in our daily life. So Flink has been proven by the industry to be the de facto standard of data streaming processing. Typical scenario are that data will be processed by Flink and sync the result into OLTP database, and then will be consumed by the online applications. And another one is to sync the result into OLAP database, and then will be consumed by offline analytics applications. So being the standard, we are thinking, are we hitting the limitation of Flink? Well, my answer is no, not even close to. And at that time, we are seeing a much bigger pictures. So before we move forward, let's take a look at the Flink architecture. As we all knew, there's a lot of great features provided by Flink, like stateful computations, like exactly one semantic. But for me, the most interesting part is batch and stream unification. And the batch is a special case of streaming, and the same engine can process both bounded and unbounded data. Since Flink works so well with streaming, I'd like to put the focus on the batch. So the question is, where can I find the most batch data processing? Anyone know that? Data warehouse, right? Data warehouse. So with data warehouse, structured data will be processed by ETL, and the data will be consumed by other applications. And since the data platform is developing, especially when the AI requirements are rising, Lakehouse, data lake has been developed to store more raw data, like unstructured data, semi-structured data, and also including structured data. And Lakehouse is an evolution on top of data lake. It combines the best part from data warehouse and data lake, and it offers flexibility, scalability of data lake, and then offers on top of that the metadata and table format. So when we put DataStream with data warehouse and Lakehouse together. And we can see that the data warehouse and Lakehouse offers daily or hourly data latency. And the DataStream offers second and even millisecond data latency. And as we can see, there is a gap, right? So when we talk about the data processing, there are always two major factors to be considered: the cost and latency. I'd like to put everything together into this data processing triangle to describe all the things. If we care more about the cost, we will choose Lakehouse. And if we care more about the latencies, we're going to use real-time stream, right? So there are obviously use cases that can only be served by real-time stream. And in this case, you can go with real-time stream. But there are many, many other use cases that are handled by batch data processing and be handled by the Lakehouse. So when the business is growing, you might want to improve the data latency. So the first thought is to migrate from Lakehouse to, can I move back? To a real-time system, right? But the cost is extremely high, so does it make sense? So I used to work in a giant companies. There are hundreds and thousands batch jobs are running with very few real-time stream jobs. So people are complaining because there's no material streaming infrastructure. So we don't know that we can rise real-time business requirements. And other side, this other guy in the platform area answers the question, oh, we are not really sure because the stream jobs are commonly very expensive. I don't know if it makes sense to spend so much money in one shot to build the whole streaming infrastructure. So it looks like for me a chicken egg problems. With no streaming infrastructure, there's no business requirement. And with no business requirement, there's no streaming infrastructure. So is there any better solutions and cost-effective solutions to solve these problems? And for me, the Streamhouse. Streamhouse can solve that loop. So you can consider a move from Lakehouse, upgrade from Lakehouse to Streamhouse with near real-time latencies and with the cost-effective solutions. So with the source of data processing triangles, we are going to have data processing architecture evolution pattern, LSR, which stands for Lakehouse, Streamhouse, and real-time system. So the cost goes higher when the architecture evolves from Lakehouse to Streamhouse and then to real-time system, real-time stream. And the benefit of using Streamhouse is that, first of all, the improvement of the latency from day to minute is much more significant comparing to the increased cost from Lakehouse. And second, since Flink SQL has been used, it is quite easy to move from Streamhouse to real-time stream back and forth, depending on the change of your business requirements. So there are commonly 4 major components for almost every data processing pipelines: the data ingestion, data computation, metadata, and storage. And both real-time stream and Lakehouse have their own concept. Lakehouse leverages the batch, everything batch ingestion, batch processing, batch data format, and data will be stored in object store. While with real-time stream, stream data will be ingested, and CC data will be supported. And there are some additional services like schema registry to manage the schema, and data will be stored in the expensive message system. So Streamhouse is just in the between, right? And data will be ingested and processed both in batch and stream manner. And the table format should follow the stream concept. And the data will be stored normally in the tiered object store. But for common cases, the cost-effective object store is good enough. So when we talk about implementing the Streamhouse, it turns out that Flink is a perfect fit for the computation engine because of its batch and stream unification. And around Flink, we created Flink CDC to support unified batch and stream data ingestion. And then we built Paimon to become the stream native data lake platform. So let's make a deep dive into each of them. Flink CDC is the first component of Streamhouse tech stack. It enabled the unified batch and streaming data ingestions. It supports most mainstream database. The switch between initial load and incremental load is seamless and log-free, which means extremely good performance. And Flink CDC provides a lot of great features based on real business requirements. For example, full database sync, schema evolution, or sharded tables consolidation. So in order to move Flink towards Streamhouse, we are not only shaping the engine, but also focusing on this batch and stream unification. For example, for SQL enhancement, we provide dynamic partition pruning and runtime filters to avoid unnecessary data I/O and network data transmission. And we offer operator fusion code generator to optimize the usage of modern CPU. And in addition to that, we create a lot of APIs to follow the Lakehouse concept. Let's take more let's see more details about engine and SQL improvements. So checkpoint duration is one key factor for end-to-end latency. A shorter checkpoint duration means lower latency for transactional sync, and more predictable checkpoint interval for to ease the daily operations, and less data to recover during the failover. So there are two major factors to improve checkpoint durations. The first one is barrier travel time, and the second one is time to take a checkpoint. The community did a lot of optimizations based on those two factors. Online checkpoint reduce the barrier travel time, but increase in-flight data as a set effect. And buffer debugging leverage the dynamic buffer size management. It can reduce both barrier travel time and in-flight data. And incremental checkpoint takes advantage of a RocksDB LSM tree. It only copies the newly created SS table files, which means reduce the size of checkpoint. And we are moving one step further. The GIC, which stands for generic log-based incremental checkpoint, it introduced a new state change log, which will reduce the checkpoint duration even further, which means even shorter checkpoint intervals. Statistics shows that GIC can provide 5 times faster checkpointing, and the incremental file size reduced by unbelievable 95%. And hybrid shuffle is the key feature of batch and stream unification. The pipeline shuffle provides a good performance, but requires a lot of resources, because all tasks that interconnect with each other need to be launched in the same time. It is tempting to use pipeline shuffle in the batch execution mode, but it is very challenging in the production environment where there's no guarantee of resources. When tasks compete with each other for resources, there will be even deadlock. So to address these issues, we developed a hybrid shuffle, which combines the advantages of blocking shuffle and pipeline shuffle. So the streaming shuffle will be used when the resource is sufficient. So all connected tasks will be launched in this, simultaneously. And it will fall back to the batch shuffle in the same time when the resource is insufficient. In this case, the resource will be used very effectively for shuffle acceleration. And with Flink 2.0, the community plans to upgrade the state storage management system to a fully separation, storage, and computation architecture to adapt to the cloud-native environment. Currently, the state of Flink job is stored in the local RocksDB files, and only the incremental file will be persist on the remote storage to make sure the complete state will be persist on the remote storage. And in the future, the Flink state will entirely reside on the remote storage. All the local hardware like storage, disk will be only used for acceleration and caching. There might be some additional optimizations like hash index, like sorted index to use to provide even more performance. And the data with different temperatures will be stored in memory, in disk, to offer the best access performance. One of the major goals of Flink 2.0 is to execute the API evolution. In order to show you a clear picture, I divided the API into 4 different groups, like low-level APIs, DataStream, process functions, high-level APIs, SQL, table, catalog, connector APIs, source functions, sync function, and operation APIs, matrix configuration, and RESTful web APIs. So the API evolution contains 2 parts. The first part is the breaking change, which cannot be done with Flink 1.x because we have backwards compatibility guarantees. Things like we want to move all the legacy APIs like dataset, source function, sync function, table source, table sync, like to remove all the duplicated classes, field methods from Java API, remove all the duplicated matrix configuration and RESTful APIs. So the second part is to redesign the API. For example, the curable state API will be redesigned after the disaggregated state has been developed. And the DataStream API will be refactored based on new process functions. And there will be no internal dependencies and no expose of internal APIs. Flink is known as a data streaming engine. It is a great framework to handle some low-level data processing. But for most common cases, Flink SQL is recommended. So why SQL? SQL is a high-level declarative APIs. It lets users to focus on their own business logic with their strong domain expertise. Something like field engineering in the AI industry, user behavior analytics in the e-commerce industry, clinical research in the healthcare industry. All those use cases require very strong domain expertise. So those users do not care about the complexity of the technology underneath. They want to focus on their own work. So on the flip side, by leveraging SQL as an abstraction, Flink has enough room to do the optimization underneath. So this is kind of a win-win setup. Users focus on their own business, and Flink will laser focus on the data processing and on the continuous optimization. So Flink already provides a lot of SQL syntax like DDL, DML, aggregation, joins, a lot. But however, not everyone knows how powerful Flink SQL is. In order to provide a clear big picture for you, I divided SQL into 4 different categories. Let's go through all of them one by one. The first one is OLTP SQL. It's a common data manipulation and query. OLAP SQL for analytics and data warehouse ETL process. And Stream SQL, it's for the typical streaming logic like Humble, Hub, Window. And Lakehouse SQL to follow the data lake concept, like create table as select. So after talking about Flink CDC and Flink itself, let's take a close look at the storage platform of Streamhouse. So Apache Paimon was born as a sub-project in Flink called Table Store, and it had become now a top-level Apache incubator project. the table format in Paimon is highly inspired by Apache Iceberg. So the concept of like snapshots, manifest files have been used too. But the underlying data structure is based on LSM tree, which is obviously streaming oriented. This kind of architecture enables Paimon to become a unified batch and stream data lake platform with many exciting features. So first of all, Paimon supports both stream read-write and batch read-write. And Paimon leverages the cost-effective data lake storage and offers the scalable metadata. And Paimon offers rich merge engines. For example, deduplication to get the last entries, partial update, and aggregation. And last but not least, Paimon simplifies the streaming pipelines by introducing a new changelog producers. There are a lot of patterns with these changelog producers, like use direct the input, or lookup, or full compactions. So this is the common data pipelines to put everything together. Data will be ingested from the source to the operation data store, and then transformed to data warehouse details and data warehouse summaries. And when we take a closer look at these data pipelines, there are many interesting scenarios. The first scenarios to use the Flink CDC and the Paimon table to do the CDC data ingestion. The good thing is, on one side, it supports CDC data ingestion, and on the other side, you can continue use your current data processing. Use Spark to read the data and do the further data processing in the batch way. The second scenarios, you can move one step further, use the Flink C code to do the streaming pre-processing, transform the data from ODS to DWD, and then let OLAP engine to consume the data from DWD. In this case, the end-to-end data latency will be reduced significantly. And the scenario 3, you can use the Flink C code to do the end-to-end streaming ETL. In this case, you're going to use one technology to solve all kinds of data processing requests. In this case, it will improve your efficiency for both development and operation. So as I mentioned previously, we are care about the cost, and we're caring users' cost. With this architecture, you can see how flexible it is. So you can do your upgrades at your comfortable pace, and you can do your upgrade based on your real business requirement, and you can do the upgrade based on your current Lakehouse, step by step, gracefully. So we figured out that there was a gap between Lakehouse and DataStream, and we defined the Streamhouse, and we shape Stream Engine, create Flink CDC and Paimon to implement the Streamhouse. And then we have this LSR data processing architecture. It is a evolution architecture driven by the business. So it is flexible. So there's obviously some use cases you have to spend money and go with real-time streaming directly. But there are also many other use cases that are currently handled by the Lakehouse. This is your starting point. So when the business is growing, you might consider to get more fresh data. And then if you care about your cost, and according to the current global economy, you should care about the cost. You can consider using Streamhouse. It can be used out of the box. Like I said, we have concept, we have implementation. You can use it directly. And the work at Ververica, we did a lot of work at Ververica. It shows that if you can stick, or you can live with the minute latency, Streamhouse can reduce the cost by 80% comparing to the real-time stream. And by using the stream pre-processing, the Streamhouse can provide 5 times better write performance and 8 times better query performance comparing to the traditional batch Lakehouse. So with all this sauce, I talked together, and we built the next generation cloud native data platform, Ververica Cloud. And Ververica Cloud offers a very open and flexible architecture. We support fully managed, semi-managed, and on-prem deployment. And with this architecture, we built an abstraction on top of diverse cloud providers. So because different users will store the data in different cloud providers. And we don't want to ask our users to move data back and forth. So we come to our customers. We build the abstractions. The user can use the same platform to run their data everywhere where the data is stored. And Vera, as Alex mentioned, is our engine. We provide better performance. And there's a lot of amazing features we have now and we offer now. We were considered to contribute back to the open source Flink in the future. And at the platform level, we provide a lot of services like autopilot. It will use your own data and train your own AI model that can be used to schedule your resources for your own usage, which means, again, save money. And advisors contains all the troubleshooting experience we have from the past 6 years. And it will give you hints and suggestions when you have some problems with your Flink jobs. Again, save your money. There are a lot of different services. I don't want to go through every one of them. So as I said, we are a cost-effective data platform. We offer very flexible pricing model. We have pay-as-you-go reserve capacity depending on your business requirement. And for big companies, you can even bring your own cloud and connect with our ecosystem. And the most important part is, on top of that, from the concept level, Ververica Cloud supports both real-time stream and Streamhouse. So if you have money, you can go directly with real-time stream. It's fine. It's where we came from. We are the masters. But if you want to save money, you care about the cost, you can go through first with Streamhouse. And yeah, I'm happy to announce that Ververica is the original creator of Streamhouse. We know everything. We contribute everything. So if you heard anything about Streamhouse in the community, the feature is coming from us. So yeah, last one, as Alex mentioned, we launched the first major release after GA. And you can feel free to scan the QR code, get 400 credits. It's free. So you can use the credit to try our features. And important is, if you have jobs on your data platform, on your Lakehouse, you can use this credit to build the same job and compare with exactly the job in your Lakehouse to see the difference. Yeah, thank you for your attention.